Organic chemistry part 2. We're going to talk about some physical properties of organic compounds, and also we're going to talk about isomers. Okay, but first, let's talk about physical properties, and to do so what we're going to look at is how these physical properties change as the molecular mass of a series increases. These are called homologous series, and they differ from other members of the series as you go up by just a CH2 group. Okay, so if we look at examples of this, we have one series, the alkane series, okay, starts with methane, ethane, propane, butane. Hopefully you can see how those structures differ as I go up through the series. And then of course we also have another one, alcohols, with the alcohol grouping. And again, hopefully you can see as we go up, we add that CH2, making the molecular mass larger, and also the electron cloud. Okay. Thing that you have to remember that a lot of these physical properties of these different compounds, such as boiling points, melting points, have to do with the intermolecular forces. Remember, there are 3 of them: London dispersion, spell it right, dipole, and hydrogen bonding. And we'll talk about these. If you don't remember those 3, don't remember the differences between those three, please pause this screencast, go back and look at your notes, go back and look at prior screencasts, particularly in the bonding unit. Okay? So, boiling points. Boiling points are going to be determined, I should say, or affected by the IMF, and the IMF, intermolecular forces, are going to be affected by the length of the carbon chain, as well as the functional groups that are present. What is the effect of the length of the carbon chain? Well, if we look at the series of alkanes, okay, as our number of carbon atoms increases, going this way, you can see that the boiling point also increases going up. Now, why might that be? Okay, as your carbon chain gets longer, okay, and I'm going to just not draw the hydrogens because I'm being a little lazy. Think about, you've got this compound, right? Next to it is a similar or the same molecule. Okay, and it's got areas of which those London dispersion forces are going to be attracted to each other, instantaneous dipoles. You've got a longer chain molecule. Okay. This has more areas that it can be attracted to it. That polarizability of the cloud, okay, increases as that length increases, which is why you will see an increase in the boiling point as the carbon chain increases. Okay. The longer the chain, the higher the boiling point. That's due to the greater polarizability of the electron cloud of the longer chain, giving us stronger intermolecular forces between molecules. Okay, let's look at structural isomers. We're going to take another look at these, but what this is molecules with the same molecular formula but different structures. These are structural isomers. Okay. Now, these are all nonpolar compounds, so the only intermolecular force present is going to be your London dispersion. If we look at the shapes of these compounds, okay, and remember, when we talk about boiling point, we're talking about a pure substance, so the substance is only made up of these molecules. So if I have a bunch of pentane molecules next to each other, hopefully you can see, again, this is a long molecule, many places for this cloud to be setting up instantaneous dipoles and being attracted. If I make it more spherical, and I'm going to look at this one because it is the most spherical out of these isomers, hopefully you can see that there's less places for these molecules to be instantaneously attracted to each other through those London dispersion. What will that lower intermolecular force have an impact on that boiling point? Well, let's look at the actual boiling points of these different substances. As you can see, the boiling point, the temperature at which this will go from liquid to gas, decreases as those spots for the intermolecular forces decreases. All right, so your intermolecular force is less with a circular, spherical molecule than it is with a straight chain. Your boiling point decreases. What if there are other intermolecular forces present? For instance, solubility in water. This is going to be determined by polarity. Remember, water being a polar substance, likes dissolve in likes. Higher polarity gives you a higher solubility in water. If we look at ethanol, which is shown, and 1-hexanol. Hexanol is only slightly soluble in water, whereas ethanol is soluble in all proportions. So that means anywhere from 0.5% to 99.5% ethanol in water is fully miscible with each other. And if we look at the portion of the molecule that would make it soluble in water, it's going to be the polar part of that molecule. It's going to be this grouping, okay, because this is what is going to allow water to hydrogen bond with these two molecules. If you look at the portion of the molecule that is polar here, it's quite a large part of that whole molecule. This molecule, that polar part, is much less of the overall. Okay? So it actually is very small compared to the nonpolar part, and that's going to contribute to it being less soluble. Okay? So the longer the C chain of an alcohol, the lower the solubility of that compound would be in water. An important thing that we're going to find when we start talking about the reactions of organic compounds is classifying alcohols and halogenoalkanes, meaning alkanes that have a halogen, group 17 atom connected to it. And they're going to be classified depending on how many R groups are on the carbon that is attached to the functional group. Okay. In a primary alcohol or primary halogenoalkane, the carbon is bonded to one alkyl group or an R group and two hydrogens and then the functional group. And you can see the same structure with the halogen attached to that carbon. A secondary has two R groups, hey, two secondary, and same with the halogenoalkane. And then tertiary, there are three alkyl groups bonded to the carbon atom that is bonded to the functional group. Remember that R group can be a methyl, an ethyl, propyl, any of those groups with the carbon. And we'll see that the structure of these R groups are going to affect how this functional group reacts in reactions, which is redundant. All right, so it's kind of an odd thing that you're throwing in here. I want you to remember this. We're going to use it later. So it's kind of defining a term that we're going to use much later. All right, let's get talking about reactivity of the alkanes. The carbon to carbon and the carbon to hydrogen bonds in an alkane are relatively strong. It is really, they're considered nonpolar molecules. Okay. These can readily undergo combustion with oxygen, and it can undergo substitution reactions with halogens in the presence of high energy UV light. So you need this energy input in the form of UV light to get the reaction started. Okay? They typically don't do much if you just have them in a container. Relatively low reaction. Okay. We will talk in much greater detail about the different types of reactions in another screencast.